All right, we're on section 1.5, talking about infinite limits. Infinite limits are the same thing as a vertical asymptote. All right, we're talking about anytime the function value approaches either infinity or negative infinity as the x value approaches some specific number, which is the same thing as what a vertical asymptote is. All right, it's a limit which increases or decreases without bound as x approaches 0. That's called an infinite limit. So we're going to talk about vertical asymptotes, and this is most of this, if not all of it, is review from either Algebra 2 or Pre-Cal, so it's still good to talk about it. We have two examples here. We know we get a vertical asymptote anytime the denominator is equal to 0. Sometimes that's very easy to see just by looking at it. Here I have x plus 1, a factor of x plus 1, and I know that if x equals negative 1, this quantity is 0, and 2 times 0 is 0, so that would give me a 0 denominator and a non-zero numerator. So I know that I have a vertical asymptote at x equals negative 1. The example to the right, we want to know when this denominator is going to equal 0. So there's a couple ways we can do that. We could add 1 and take the square root, or we could factor this. And then, of course, set each factor equal to 0. So x plus 1 equals 0 gives us a negative 1 solution. X minus 1 equals 0 gives us a positive 1 solution. So we know that we have a vertical asymptote. In other words, this denominator would equal 0, and the numerator would be non-zero when x equals negative 1 or 1. We also need to think about vertical asymptotes for trig functions. So we're talking about cotangent of x here. We know that the cotangent of x is defined as the cosine of x over the sine of x. So we know that we're going to get a vertical asymptote whenever the sine of x equals 0. And we know from our unit circle that the sine of x equals 0 anytime x is equal to some integer factor of theta. I'm sorry, of pi. So we have x equals k pi. We just generalize it that way. We could also write it as pi, 2 pi, 3 pi, and so on. So any integer multiple of pi is going to give us a denominator of 0, and we know the cosine won't be 0 in that place, so we're going to get vertical asymptote for cotangent of x there. Example 4, we have x squared plus 3x minus 18 over x squared minus 9. We're trying to find the vertical asymptotes here. So we know that we want the denominator equal to 0. Right? As it's written here, it has 2 factors in the numerator and 2 factors in the denominator. Right? Notice that there's 2 discontinuities here, but only one of them is a vertical asymptote. So because we can factor numerator and denominator, and we could cancel out the x minus 3's, that x minus 3 gives us an x equals 3 whole. That is a removable discontinuity. We can factor and cancel out. That gives us a whole or removable discontinuity at x equals 3. This x plus 3 factor cannot be canceled out, so that gives us a vertical asymptote at x equals negative 3. All right, on to the next page. We have the properties of limits at the top of the page, and here we're going to determine the following limits. So we want to determine the limit as x approaches 0 of 1 plus 1 over x squared. So we're going to split that up into its, we're going to use the sum and break it up into the sum of 2 limits. So we have the limit as x approaches 0 of 1 plus the limit as x approaches 0 of 1 over x squared. So the limit of 1, no matter what we do with x, 1 is 1. So that limit is 1. As x approaches 0 here, we're going to get really close to 1 over 0. So that infinite limit is going to be positive infinity here. So 1 plus infinity just gives us infinity. Second example here. We want to know when, as x approaches 1 from the negative side, what's going to happen to x squared plus 1 over the quantity 1 over x minus 1. So this limit is 0. We get a 2 over, this turns out to be a negative infinity, and we'll talk about why that's the case in a second. But we get 2 over any finite value over an infinite value is always going to give us a limit of 0. And here's why. We break that down. So we break those down into look just at the numerator and denominator. So the limit of x squared plus 1 as x approaches 1 from the negative, we just use substitution. 1 plus 1 is 2. And we see here that when we approach 1 from the negative side, so we're going to have our x values are always going to be slightly smaller than 1. So when we do that, we're going to get a value that's slightly smaller than 1 minus 1. So this is always going to be a negative value. So as x approaches 1 from the negative, this denominator is going to get closer and closer and closer to 0, but always be slightly negative. So we get a 1 over a very, very, very small negative number, and that limit approaches negative infinity. Right? In the case of the overall limit, it really doesn't matter because we have a finite positive value here over an infinite value, and that's 0, or the limit of that is 0 at least. But in the terms of just this denominator, the limit of this denominator, it does matter. We have to think very carefully about whether this limit's going to be positive or negative infinity.